Hello guys, welcome to the part 3 of conduction. Okay, after completing this lesson, you are expected to be able to derive equations for spherical and cylindrical systems. You are also expected to be able to represent a heat transfer problem using heat circuit, which is a very important technique that you must master so that you'll be able to solve the heat transfer problems. Okay, firstly, let's continue our equation derivation. So in our previous lecture, we have gone through case 1 and case 2 for flat plate with and without heat generation. We are going to skip case 3 first. Okay, proceed directly to case number 4, which is a cylindrical system without heat generation. Okay, before we start the derivation, let's have a look on our system, which is a cylinder. So we see that this is a cylinder with R1 and R2. So at R1, the temperature is at T1. Then at R2, temperature is at T2. Okay, and because of that, we have the following boundary conditions. R equals to R1, then T equals to T1. At boundary condition 2, we have R equals to R2, then T equals to T2. Okay, the difference between this system as compared to the flat plate is, okay, let's have a look. So our flat plate system, okay, in our flat plate system, we see that when x changes, the cross-sectional area A remains constant. Okay, meaning A remain constant. If x change, A doesn't change. But for the cylindrical system is different. As you can see, you learn in high school, the cross-sectional area, okay, of a cylinder actually equals to this formula. A equals to 2 pi r L. So where is L? L is the length of the cylinder. Okay, so when R changes, okay, A also changes. Typically when R increase, then A also increase accordingly. So this is the major difference, and we must take this into consideration when we derive the equations. Okay, so now let's start deriving for temperature profile, TR. Okay, so let's see the assumptions. Okay, the assumption. We consider heat transfer in one direction only, that is in the radius direction, meaning we only consider heat transferred through the radius. Okay, through the radius. Because of that, the term in the energy balance equation for heat transfer in other directions, the direction other than R, will becomes 0. Okay, and the second assumption is we don't consider there is heat generation, meaning G in this case is equal to 0, and because of this term also equals to 0. And we consider a system under steady state, and because of this term also becomes 0. Okay, and the result is the overall equation of energy balance equation is simplified, becomes this, and because under such condition temperature only depends on radius. Okay, and because of that the PDE can now be simplified into an ODE. Okay, so delta now becomes D. Okay, so we will start deriving from here. Okay, so now let's integrate this equation 2 times. Okay, let's do the first integration. Then we get r dt over dr equals to, when we integrate 0, we get a constant. Let's term it as c1. Now we need to rearrange, so move the r to the right side of the equation. Then we will get dt equals to c1. Then here we have 1 over r dr. Integrate both sides, then we get tr equals to c1. Here we get ln r plus another constant. Let's terms it at c2. So we will get equation number 1. Okay, in order to solve, now our next step is we need to solve for the two constants c1 and c2. So how to solve it? We need to come up with two equations, okay, based on boundary condition 1 and 2. Okay, with the two equations, then we solve it simultaneously, then we can get the value of c1 and c2. So let's do that. T1 equals to c1 ln r1 plus c2. Okay, let's term this as equation number 2. And T2 equals to c1 ln r2 plus c2. Let's term it as equation number 3. Okay, so and how to solve it simultaneously? Let's use equation number 3 to minus equation number 2. Then we can get rid of c2, then we can get c1. Okay, when doing so, we get t2 minus t1 equals to c1. Inside bracket we have ln r2 minus ln r1. Okay, rearrange everything. Okay, we will get t2 minus t1 equals to c1 here. Let's simplify it. Ln r2 over r1. Then we will get c1 equals to t2 minus t1 divided by ln r2 over r1. So now we have solved for c1. Then we now want to solve for c2. What to do? We substitute c1 into equation number 2. Okay, then we get t1 equals to t2 minus t1 divided by ln r2 over r1 r times ln r1 plus c2. Okay, then we will get c2 equals to t1 minus t2 minus t1 divided by ln r2 over r1 times ln r1. Okay, so now we have solved for both c1 and c2. So next, what we need to do, we can now substitute c1 and c2 into equation number 1. That will give us tr. So tr equals to, where is c1? c1 is t2 minus t1 divided by ln R2 over R1 times ln R plus C2 equals to T1 minus T2 minus T1 divided by ln R2 over R1 times ln R1. Okay, then we rearrange everything and factorize. We will get TR equals to T2 minus T1 divided by ln R2 over R1 times ln R over R1 plus T1. Okay, and this is the equation for temperature profile over R. Okay, now let's move on to deriving equation for QR, starting from Fourier's law. Okay, so QR equals to negative, and we know A for this case equals to 2 pi R L K dt over dr. Okay, now we need to rearrange. We need to move R and some constant to the left. Okay, so with this we will get QR divided by 2 pi L. Okay, then we have 1 over R here. Okay, equals to negative K. Okay, and here we have dt and dr is here. Integrate both sides. Okay, according to boundary condition 1 and 2. So it's from R1 to R2. Okay, then temperature at R1 is T1, temperature at R2 is T2. So we integrate both sides. This is what we get. QR equals to 2 pi L. Then inside the bracket we have ln R2 minus ln R1 equals to negative K T2 minus T1. Okay, now let's rearrange. So we will get QR. Okay, then here inside the bracket we have ln R2 over R1. Okay, we move this inside the constant 2 pi L equals to here we want to get rid of the negative side, so what we do is now inside the bracket is T1 minus T2. Okay, then rearrange, we move everything to the right, then we get QR equals to K T1 minus T2 divided by ln R2 over R1 divided by 2 pi L, and we move K to this part. Okay, T1 minus T2 divided by ln R2 over R1 divided by 2 pi L K. Okay, so that this equation is in the form of driving force divided by resistance. Okay, so yep, this is equation for heat transfer rate for hollow cylinder. This is an exercise for all of you. you are required to do derivation for a spherical system. Okay, please complete this exercise and submit it to your lecturer. Okay, and before we proceed to deriving equation for case number 3, multi-layers, I would like to introduce you a very important technique which you really need it for this course. That is to represent heat transfer problem using circuit diagram. So in order to do that, we need to do some revision. Okay, what you have learned in high school, physics. Okay, you learn this V equals to IR. This is Ohm's law. Okay, so it can also be represented in this form, I equals to V over R. So actually you see there is a similarity between what we have learned. Okay, because we learned that Q, heat transfer rate, equals to temperature difference divided by heat resistance. Okay, so you see current is actually rate of electron transfer. Okay, rate of electron transfer in the circuit, and voltage is actually differences. Okay, differences in terms of electrical potential. Okay, so voltage is the driving force that enables the electron to flow and form current. Okay, so you see there is a so-called equality, okay, between the two system, the two equations. Okay, that's why with this basic we are going to use electrical circuit. We can use electrical circuit diagram to represent heat transfer problem, which I'm going to explain further. And we also learn in physics that there are two types of circuit. The first type is called series. The second type is called parallel. So what makes the difference? The difference lies in how the current pass through the resistances. So in the series, so the current pass through resistances R1, R2, R3 one by one. Okay, we will first pass through R1, followed by R2, followed by R3. Whereby for parallel system, you will see the current will be divided here. Okay, and it will pass through R1, R2, and R3 at the same time. Okay, and because of this difference, we also have different formula for counting voltage, okay, for counting total resistance in the system. Okay, so when we encounter a heat transfer problem, our first task is to identify whether the system falls into a series system or is a parallel system. Okay, so how to do that? I'm going to show you in the next example. Okay, let's go through this example. It's a system consists of 3 layers, and what you can see here, the 3 layers consist of different materials and with different thickness. Okay, layer number 1 is a material with the thickness of delta x1 and thermal conductivity of K1, and so on for layer 2 and layer 3. And the information also provided here on the outer surface of layer 1, the temperature is 100 degrees Celsius. So we will term that as Ti. Okay, and meanwhile for the outer layer of layer number 3, okay, this is the temperature on the surface, outer surface. The temperature is 20 degrees Celsius. so let's term it as T naught. Okay, actually you also have temperature on the interface between layer 1 and layer 2, that is T1. Meanwhile, the temperature between layer 2 and layer 3 on the interface between layer 2 and layer 3, the temperature is T2. Okay, so what this which kind of system these three layers belong to? Okay, so we need to first ask ourselves so we know that heat will be transferred from here, the first layer, to the third layer because of temperature difference. So when the heat is transferred, so in this system it's very obvious, it will first pass through layer 1, followed by layer 2, followed by layer 3. Okay, so it's very clear this is a series system. Okay, so that's why the circuit diagram looks like this. Okay, so let's analyze one by one. So as you can see here, okay, there is an overall Q. Okay, you see the overall Q. So this is the overall Q because the overall Q take Ti and T naught into consideration. Okay, and there is also Q1. So Q1, so here we have Q1, then here we have Q2, and here we have Q3. Okay, and we can see actually this part, the first part of the circuit, okay, from Ti to T naught, okay, represent the first layer, while the second part of the circuit, okay, from T1 to T2 represent the second layer, okay, while the third part of the circuit, okay, which is from T2 to T naught actually represent the third layer. So this is how you can understand this circuit diagram. So and after this, you are required to every time, I think almost every time when there is a heat transfer problem, you need to translate that system into a circuit diagram like this. Okay, it will enable you to do the calculation much easier. Okay, and now let's focus on the resistance of each layer, R1, R2, and R3. So we know that this is a flat plate system, okay, with constant cross-sectional area. So we learned in the previous lecture that for such system, Qx equals to delta T divided by delta X over A K, and this part is the R, is the resistance. Okay, and why you don't see A here? Because A is constant, so since it's a constant, so we take it out, okay, and put it here. Okay, so it becomes Q over A, meaning it's a flux. Okay, so we only take the variables into consideration. So that's why you see R equals to delta X over K. So R1 equals to delta X1 over K1. So and so on for R2 and for R3. Okay, now let's see a few more things regarding this system. Okay, first is this circuit, can actually be simplified into this. Okay, if we see this whole system as a whole, okay, as a whole, meaning we see this as a whole like this. Okay, so here we have Ti and here we have T naught. Okay, and the Q we will get is Q, overall Q. Okay, then the J here is the Rj. Rj we know for a series system it equals to R1 plus R2 plus R3. Okay, as you can see here, this is Rj, so this is R1, this is R2, and this is R3. Okay, and we also know that for series the overall Q, okay, is actually equals to Q1, equals to Q2, and equals to Q3. So that's why the 4Q are actually the same. Okay, they are actually the same. So as you can see from this, this is actually equals to overall Q. Okay, because we are referring to Ti and T naught. So Ti is here, T naught is here. Okay, so it's overall. Then this is actually Q1 because we are referring to Ti and T1. T1 is here. Okay, T2 is here. Okay, so this is actually Q1. Okay, and this is actually Q2, and this is actually Q3. Okay, one more important thing we can see from here is, let's say, because now only Ti and T naught are given, but T1 and T2 are not given. But based on this equation, we can actually obtain T1 and T2. Right? We can actually obtain T1 and T2 because let's take T1 for example. Yeah, let's see. First, we use we can use a formula. Okay, we can use this formula. Okay, we can use this formula because all this information, thickness, thermal conductivity are given, are provided. Okay, so we can get Rj. Okay, because we have Rj, we also have Ti, we also have T naught, so we can get overall Q. And we know that for series, overall Q equals to Q1 equals to Q2 equals to Q3, and meaning Q1 equals to overall Q. So and we have R1, we also have Ti, so using the value of Q, then we can get Ti. Same goes to temperature of T2. Okay, so I hope now you see. Okay, if we are able to convert our heat transfer problem into a circuit diagram, so it will really help us, okay, in determining many values, many properties which we want to determine. Okay, it's very useful. I think we are ready to proceed to case number 3, deriving equation for multi-layers. Okay, so actually this is similar with what we have done for the circuit diagram. So let's look at this system. It's a composite wall, consists of 3 layers. Okay, and you see each layer has different thickness and also made of different material, so with different K values. Okay, and here of course different X value, different delta X value, sorry. Okay, and the temperature given here is T infinity in and T infinity out. Okay, so let me give you a clearer picture on the context of this problem of the system. Okay, so this is a furnace. Okay, it's a furnace. So if you magnify this part, okay, the wall, so this is what you see here. Okay, so here this part is inside the furnace, this is outside, meaning at the ambient. Okay, so the temperature here given is the temperature of the ambient air. Okay, one is inside the furnace, one is outside the furnace. Okay, so now I want you to pause this video for 10 seconds and think how many resistances are there for this system. Okay, pause it now. Okay, so if your answer is 3, then I want to say sorry, you have gotten the wrong answer. So now you might have questions. It seems very similar to the last example, so why this time my answer is wrong? Okay, let me explain to you the difference between the last example. Okay, the difference between the last example, which is this one, as compared to the system given. Okay, the answer is there are actually 5 resistances. Okay, 5 resistances. Where are the 2 extra? Let me tell you. Okay, the example given just now, the T given, okay, the Ti and T naught, okay, are the temperatures at the outer surface of layer 1 and layer 3. But this one, the temperature given is the temperature of the air. Okay, this temperature of the air inside the furnace. This temperature of the air outside the furnace is not the temperature on the surface of first layer and third layer. Okay, so in order, so the temperature on the surface here is lower as compared to the temperature here, the T infinity I. Okay, and the temperature on the surface here will be higher as compared to the outside ambient temperature. Otherwise, there will not be heat transfer. Okay, if they are equilibrium, there will not be any heat transfer, right? So meaning, in order for this case, for the furnace, now in order for the heat from the air to be transferred, one more resistance. Okay, one more resistance. I need to erase it. Okay, one more resistance need to be overcome. Okay, the resistance actually comes from the air. Okay, come from the air. So meaning there is one resistance here. Then after this, first layer resistance, then second layer's resistance, then third layer's resistance. Then from the wall to the outside ambient air, there is another resistance. Okay, so meaning here you have T infinity in, and here is your T infinity out. Okay, and this is the temperature of the surface of the first layer. Okay, so I hope that is clear. And another thing I want to mention here for this example is the difference between these two. The first, as the previous example, there is only one mechanism for the heat transfer, that is purely conduction. Okay, from layer 1 to 2 to 3. But for this case, there are actually 2 mechanisms happen. Okay, here from layer 1 to 3 is conduction, but from the inside furnace, air to the surface of layer 1 is actually convection. Okay, same goes to this, from the outer surface of third layer to the ambient air, there is another convection. Okay, so for this case, it's actually a combination of conduction plus convection. So the additional two resistances actually comes from the convection. Okay, I hope that's clear. I want to highlight here for this example is that you can see for inside furnace, okay, the information provided here is HI and here is HO. Okay, but for the wall material, its thermal conductivity or K are provided. Okay, so here also give you some clue. Actually, um, for the heat to be transferred from the air to the wall surface and from the wall to the outside air, so it's another process, okay, called convection. And this H actually stand for convective heat transfer coefficient. Okay, so in topic number 2, when you learn about convection, so actually the main content of convection in topic number 2 is you need to use different formula, different techniques to determine the value of H. Okay, in conduction, in this first topic, the value of H is given. Okay, but in topic number 2, you need to use different formula to determine, to calculate the value of H yourself. Okay. Okay, and this is the circuit diagram of the system. So as we can see here, we have T infinity in, and on this surface is T1, and here you will T2, and now this one is T3, and on the surface we have T4, and the ambient temperature is T infinity out. Okay, so you can see all this temperature here. Okay, okay, I've explained this in the previous example. I guess you understand already. And okay, and this overall system can be simplified into this. Okay, because the temperature given only T infinity in and also T infinity out. Okay, and we know this is a series system. Okay, because heat need to pass by layer 1, after that layer 2, after that layer 3. Okay, so it's series. and because of that, our Rj equals to R1 plus R2 plus R3 plus R4 and plus R5. Okay, and now let's proceed to calculate all the resistances. Okay, we know that R1 and R5 are due to convection. R2, 3, and 4 are due to conduction. Okay, so they have different formulas because we know for conduction Q equals to delta T over delta X per AK. Okay, so this is for conduction. Okay, delta X over AK. For convection, Q equals to AH delta T if we convert into the form of driving force per resistance. So this is it, delta T over 1 over AH. So here, this is the resistance for convection. So that's why for R1, so the R is 1 over, okay, because here A, in our case, the cross-sectional area is constant. So that's why we take it out. Okay, we take it out. So that why we here is Q over A. So we only take the variables into consideration when we calculate R. Okay, so that's why for R1 is 1 over H, and this is infinity in. Okay, and for R5 is 1 over H, infinity out. Okay, then for R2 is delta X2, delta X1, layer 1, okay, divided by K1. Then for R3 is delta X layer number 2, K number 2. And for R4 is delta X layer number 3, then K for layer 3. Okay, so and we know this is a series, so Rj equals to R1 plus R2 plus R3 plus R4 and plus R5. So just sum all these together, then you will get Rj. Okay, then here I want to introduce you a new formula, seemingly new actually, but actually not new, because you see it's actually same. This formula is actually same as the heat transfer formula for convection. Okay, just that you see the symbol is slightly different. Okay, for heat transfer only involved in convection. Okay, the symbol or here you see only involve conduction. The symbol is small q, but here because the system, the heat transfer involve more than one mechanism, so to differentiate that we use a capital Q for that. Okay, and A is the surface area exposed, meaning in surface area involved in heat transfer. Then delta T, of course, temperature difference. So here is a new term. It's called overall heat transfer coefficient. The unit is the watt per meter square per Kelvin. So why we use U? Okay, so for convection is H. Okay, is convective heat transfer coefficient. But I have told you just now, this system involves more than one mechanism. So in order not to cause confusion, so we apply a new term for the coefficient. So that is overall heat transfer coefficient. It's called U. So if you convert this formula into the form of driving force per per resistance, you will see delta T over 1 over UA. Okay, so this is it, delta T over 1 over UA. So it's in the form of driving force divided by resistance. Okay, and because of that, R equals to 1 over UA. So this is the relationship between, sometimes you need to relate this, okay, U with R. So this is the relationship between the overall coefficient with the RJ. Before we end our video for this session, so let me give a brief summary on what we have done. So far we have done deriving equations for different geometrical shape. Okay, so we have done for flat plate. Okay, we have done for cylindrical system and spherical systems, and this is the general formula of rate of heat transfer, that is temperature difference divided by resistance. And for different geometrical shape, okay, the R has different formula. Okay, so this is for flat plate, this is for cylindrical system, and this is for spherical system. So you need to be careful. Okay, you need to know which formula to be used, and if we have sometimes multiple layer, okay, then we need to use circuit diagram. Okay, then sometimes the multiple layer not just limited to flat plate, of course, because the example we have gone through is based on flat plate, but sometimes you will encounter whereby, let's say for cylinder, this is quite common also in industry. Let's say you have pipe. Okay, you have pipe, so this is a pipe, and outside the pipe there is a layer of maybe insulation. Okay, so this is also multi-layer system, right? Okay, so you need to use circuit diagram to represent. So R1, R2, so this how you do that. Okay, and let's say if we want to consider if the temperature given is temperature inside, okay, and temperature at outside, then it means you have 4 resistances, right? You have 4 resistances, R3 and R4. Then you need to use circuit diagram to represent this so that you can get RJ. Okay, and when the whole system, when the heat transfer system involve more than one mechanism, meaning not just conduction or not just convection, then you need to use this overall coefficient, okay, to calculate the Q. Okay, and you need to know the relationship between the RJ and the overall coefficient. Okay, I guess I have summarized what we have gone through. So thank you for your attention. So we will continue in the next topic.